Hey guys, in this video we're going to go through 3 exercises which are fundamental in proofs by contradiction. Sometimes when we're proving by contradiction we use the fact, for example, that no number can be even or odd at the same time. So we have something like the left hand side is even, the right hand side is odd, so this is a contradiction. Now that strategy works due to this exercise number 1. The foundation is in this exercise number 1. No integer can be both even and odd at the same time. So a few things that we take for granted will be proven in this video. Also, if you take a look at exercise number 2, for example, if n squared is even, then n is even. This is a strategy that we use when we are dealing with the classic proof by contradiction. Prove that root of 2 is an irrational number. So this is something that we rely on. We rely on this precise fact. And for exercise number 3, for example, this one, if n squared is a multiple of 3, then n is also a multiple of 3. This is useful when proving, for example, that root of 3 is an irrational number. So these are foundation, extremely important exercises that you should know how to handle, how to prove. So let's go through all of them. Starting with exercise number 1, prove by contradiction that no integer is both even and odd at the same time. So if you remember the 5-step process, and hopefully you do when proving by contradiction, by the way, you can find this cheat sheet in the website or in the description of this video. The 5-step process involves the following steps: stating the proposition, what we're proving to be true, right? Then we assume the negation is true, not P is true. We develop the proof, we get some sort of nonsense, we identify that nonsense, that contradiction, and then lastly, we conclude that by contradiction, the assumption or the proposition P is true. So those are the 5 steps. In this case, what we have as the proposition is no integer is both even and odd, which means that the negation, which we're assuming to be true, the negation is there exists an integer, which we're going to call k, for example, which is both even and odd. Now, do remember that we represent even numbers as 2 times something, so 2 times w, we can use w in this case, and odd numbers as 2w plus 1. So this k that we're referring to, this supposedly this integer, which is supposedly even and odd at the same time, is equal to 2w, but it's also equal to 2w plus 1. Now, there's a catch here. We did state that it's even and odd at the same time. There's just one thing that we need to be careful here. This even and odd number, which represents k, which is the even and odd number at the same time, nobody mentioned that these are supposed to be consecutive integers, right? So you will be wrong to start the proof saying that it's equal, this k is equal to 2w and also 2w plus 1. These would be consecutive integers, but like I said, it was never mentioned that it should be consecutive. The way to address this problem is to rewrite this k as 2w1 and 2w2 plus 1. Now, w1 and w2, they should also be integers. So again, we're saying that this number k is both even and odd. Now, if we're talking about the same k, the same number, that means that 2w1 is equal to 2w2 plus 1, which means that 2w1 minus 2w2, it is equal to 1. We can factor out a 2 on the left-hand side and divide the whole equation by 2, which means that the difference between w1 and w2 will be equal to half. Now, this is exactly where the contradiction lies. We have a difference, a subtraction between 2 integers, which is an integer. A difference between 2 integers should be an integer. Now, on the right-hand side, we do not have an integer. And this is step number 4 on the 5-step process. This is us identifying where the contradiction lies. Given that the left-hand side, which is a difference of 2 integers, is an integer, and the right-hand side is not, we have a contradiction. And this is not the conclusion. The conclusion comes right now. Therefore, by contradiction, the proposition P is true. And we do not have to rewrite p if we stated what p is before, right? Which is exactly what we did. We know that p is no integer is both even and odd. So this is the first exercise. Let's move to the second one now. On the second exercise, we need to prove by contradiction that for an integer n, if n squared is even, then n is even as well. Now, this is an if-then statement. We need to know how to deal with if-then statements in proofs by contradiction. The negation of if some statement A, then some other statement B. So if A, then B. It is A and not B. There's another video with only if-then statements in proofs by contradiction in this channel. You can search for it. There are many examples there. We dive deep into these exercises, these types of exercises, a little bit more. In this case, let's just state the fact that the negation of if A then B is A and not B. Okay, so let's start with that. Now we are going to write the proposition P, which is for a given integer n, if n squared is even, then n is even as well. Which means that the negation of p, as we were mentioning before, so in this case, there exists an integer n such that n squared is even, but n is odd. Now, what is this number n, this odd number n? N can be represented, as we know, as 2k plus 1, k being an integer as well. This is how we represent odd numbers. So let's assume that n is equal to 2k plus 1, meaning it's an odd number. Then n squared, which is 2k plus 1 squared, it is equal to 4k squared. Now we're just expanding this binomial, plus 4k plus 1. We can factor out a 2 in the first two terms of this expression, 2k plus 1. Now we have a contradiction right here, given the fact that this, which by the way is already even, but the main thing is multiplying by 2 makes it even. Even if this was odd, which is not, this is actually even as well. But even if this was odd, when you multiply it by 2, that makes it for a even integer, which means that this is even. When we take an even number and we add 1 to it, we produce an odd integer. So this n squared is odd. And this is why we got to a contradiction. We did assume that there would exist an integer n such that n squared is even. Not the case here. We just found out that n squared is odd, actually, and n is odd. So the contradiction lies on the fact that n squared is actually not even. It is odd. So which is odd, contradicting our initial statement. Therefore, by contradiction, the proposition P is true. And this is all there is to it. Now we can move to exercise 3, example number 3. Now on exercise number 3, we have proof by contradiction that for an integer n, if n squared is a multiple of 3, then n is also a multiple of 3. Again, we have an if-then statement. We need to know how to deal with if-then statements. We already know. We already did something similar previously. So let me copy and paste what we wrote before. Now, for this exercise, the proposition is for a given integer n, if n squared is a multiple of 3, then n is also a multiple of 3. The negation of that, so assume for the sake of contradiction that there exists, so this is the negation of that, there exists an integer n such that n squared is a multiple of 3 and n is not a multiple of 3. Now, what are numbers which are multiples of 3? You can think about those as numbers that can be written as 3 times something. So this is 3 times 1, 3 times 2, 3 times 3, and so on. So every time you can write a number as 3 times k, k being any integer, you are representing a multiple of 3. So these numbers, or these numbers, which are the same, by the way, they are divisible by 3. When you try to divide them by 3, or when you divide them by 3, you get no remainder. And what are the numbers in between which are not divisible by 3? Meaning for 5, 7, 8. What happens to them when you try to divide them by 3? Well, if you try to divide 4 by 3, you get, in this case, 3 times 1 plus 1 as a remainder. When you try to divide 5, you get 3 times 1 plus 2 as a remainder. When you try to divide 7, you get 3 times 2 plus 1 as a remainder. When you try to divide 8, you get 3 times 2 plus 2 as a remainder. So every time when dividing by 3, when you get 1 or 2 as a remainder, that means that the number is not divisible by 3. And that is why we can represent numbers which are not divisible by 3 as 3 times k plus 1 or 3 times k plus 2. Do notice that if you have 3 times k plus 3, that makes it for a number which is divisible by 3 again, right? So these are the only two scenarios which are possible. We're going to break this exercise down into these two cases. Again, we're assuming that n is not a multiple of 3, and we're saying that there exists an integer such that n squared, this n squared, will be a multiple of 3 or divisible by 3, which by all means is the same thing. We will get a contradiction that will not work, okay? So assuming that n is not divisible by 3, we have the two possible scenarios. Considering scenario number 1, if n is 3k plus 1, that means that n squared is 3k plus 1 squared, which is 9k squared plus 6k plus 1, which is 3 times 3k squared plus 2k plus 1. Now, this portion right here is indeed divisible by 3, or a multiple of 3. However, when you add 1, this is not divisible by 3. And let me not write divisible because the exercise actually says multiple, despite the fact that it means pretty much the same thing. Let me erase this. So we have a multiple of 3 here, and not a multiple of 3 when you consider the plus 1. Therefore, n squared is not a multiple of 3. So we have a contradiction. Now let's assume that n is 3k plus 2 now. What is n squared? N squared is 3k plus 2 squared, which is equal to 9k squared plus 12k plus 4. And we can, again, factor out a 3. And before I do that, let me just rewrite this 4 as 3 plus 1, because I want to use that 3 as well. So we have 3 times 3k squared plus 4k plus 1 plus 1. Again, similarly, we have a multiple of 3. And when you consider the plus 1, this is not a multiple of 3. So for the same reason, we can state that n squared is not a multiple of 3, therefore we have a contradiction. We have a contradiction in both cases, in both scenarios. Therefore, to conclude this exercise, you write by contradiction, therefore by contradiction P, the proposition P is true. And that's it.